Hello students, welcome to Medcom Bytes by Medcom Academy. In this series, we will solve some important MCQs which not only test your understanding of core concepts but are also potential questions for the upcoming MBBS, MD and other various competitive examinations. Let me move over to the question. This question came in a recent mock test of a medical college in West Bengal. I'm reading it out for you. In a study of a newly introduced diagnostic test for a rare disease, the test shows a sensitivity of 98% and a specificity of 95%. If the disease prevalence is 1%, what is the most likely outcome when this test is applied to the general population? The options are a high number of true positives and very few false positives. B, the positive predictive value will be very high. C, most of the positive test results will be false positive. And D, the negative predictive value will be low. In order to solve this question, we will first discuss an important concept in screening, predictive values of a screening test or a diagnostic test, and understand how these values vary in the context of disease prevalence. First of all, for the selection of an optimum screening test, a fundamental question needs to be answered. The question is, how good is a test at identifying people with or without a disease? In effect, we are asking, if we screen a population, what proportion of people who have the disease will be correctly identified? This is addressed by the values sensitivity and specificity. Right? If the test results are positive in this, now this is the practical setting where the clinician might want to know that if the test results are positive in this patient, what is the probability that this patient truly has the disease? This is given by the positive predictive value of the test. I presume that all of you already have a good understanding of these terminologies, the sensitivity, specificity, PPV and NPV. We will have a brief recap. So moving ahead, let's draw the standard 2x2 contingency table. Now I've already drawn it for you. You can see we use conventional alphabets like true positives, which means the patient or the population, this group of people already have the disease, and the test is also able to correctly identify them as the diseased. So this is true positive marked by A. Next, we have the set which is in which the disease is absent, but the test wrongly identifies them as positive. So they are actually false positives given by the letter B. Now, the third is where the disease is present, but the test is unable to identify them. So they are actually wrongly given the impression of a negative test. So it is actually false negative given by the alphabet C. And then we have the last true negatives where the disease is absent and the test also correctly identifies them as the non-diseased people. So this is given by the letter D. As we all know, very simply given by this formula, sensitivity is true positives by disease positives. So it is A by A plus C. Specificity is given as true negatives by disease negatives. So D by B plus T. Now, when we go to positive predictive value, let's understand what it is. It is the probability that the patient, the person with the positive test actually has the disease. So this is given by PPV is given by the formula A by A plus B. That is true positive by test positive. And when we go for the negative predictive value, it is the probability that a person with a negative test result actually do not have the disease in question. So this is given by the formula NPV equal to E by C plus D. So let's go back to the question again. Now in here, mark the word that the prevalence is only 1%. So this is a rare disease and the test has a very good performance. That is, it has 98% sensitivity and a 95% specificity. So arbitrarily, let us do the calculations on a population of 1,000 people who are being screened with this test with the above mentioned characteristics, right? So we go back to the 2x2 table where I just said that we will do the calculation on 1,000 persons. The disease prevalence is 1%. So people, like there will be 1% of 1,000, that is 10 people have the disease in question, while 990 people do not have the disease. Now, when we apply the sensitivity value of the test, that is 98%. So 98% of those who actually have the disease, the test is able to identify them. So 98% of 10 is 9.8%, approximately 10. When we apply the specificity figure, that is 95%. So basically, 95% of those who do not have the disease are identified by this test. So 95% of 990 is 940.5. So approximately 941. These are the true negatives. Now 990 is disease negative, 941 are true negatives. So actually 49, the difference, 49 are false positives, means they do not have the disease, but the test wrongly identifies them as positive. So you can see, right, that only 10 people are true positive, while the test gives 49 people as false positive. So basically, the test is giving a total of 59 positive results in a population of 1,000, right? So if we go by the formula, PPV is A by A plus B, that is 10 by 59, which is roughly 17%. Now, false negative, let's calculate the negative predictive value. So, this false negative is going to be 0.2, that is 10 minus 9.8.2. So, we can take it as roughly 0. Now, total test negative is 941. So, basically, negative predictive value is going to be 941 by 941, that is approximately 100%. Basically, if you go, exact values are, this is like approximately 100, exact values are 99.9%. Right. So you can see, right, despite the high sensitivity and specificity, because the disease is rare, most positive tests are actually false positives, and only 17% of the test positive results are true positives. Right. While the this test is gives a very like a very high negative predictive value, means someone who tests negative, there is a very high chance that they truly do not have the disease in question, right? Now, next, we want to understand how the disease prevalence affects the positive predictive value. So, we redo the exercise after considering the disease prevalence to be 5%. We keep the sensitivity and the specificity values as it is, and like change the prevalence figure to 5%. So, I do the calculation again for you. Like we have 1,000 people. Now, the disease prevalence is 5. So, 50 people are diseased and 950 people are disease free. 98% of 50 people who are diseased had true positives are identified by this test. So 98% of 50 is 49. So obviously false negative is 1, right? And 95% of 950 are true negatives. So after we apply the specificity figure, so 95% of 950 is roughly 903, 902 point something. So it is 903. So here the difference again, it is going to be 47. So 47 persons are identified as false positive by the test, and 49 people are actually true positive. So the total positive is 96 and total test negatives are 904. So if we calculate the positive predictive value now, it is going to be 49 upon 96. That is roughly 51%. And when we calculate the negative predictive value, it is again going to be very high, 903 by 904, sorry, which is roughly 99.89%. So now we can see, right, that as the disease prevalence increases from 1% to 5%, the positive predictive value is also increased from 17% to 51%. What are the take-home messages from this exercise? The first message is the PPV is influenced by the disease prevalence. Next, when the disease is rare, even good tests produce many false positives, thereby reducing PPV. You can already see that positive results in a low prevalence setting often leads to a lot of false positives. Therefore, if we apply a screening test, a confirmatory test is necessary. The third message is NPV tends to be very high when the disease prevalence is low. What does this mean? That a negative test result is you can reliably rule out a disease in such settings, right? From a negative test. And finally, when the disease prevalence increases, positive predictive value increases. So once again, we come back to the question and now we are going to mark the correct answer. Let's read the options again. First was a high number of true positives and a very few false positives. Is this correct? No, wrong. B, the positive predictive value will be very high. No, in this situation, it is going to be low. C, most of the positive test results will be false positive. So this is the correct option, right? And negative predictive value will be low. Obviously, we just saw that negative predictive value is very high. When we come to the practical application from this exercise, now this is important from while judging whether a screening program with a very high performing abilities like high sensitivity and high specificity, whether it will be successful if we advocate it for a disease or screen for a disease which has a very low prevalence. Actually, no, it won't be productive at all. Like you can see, right? Despite like if you are going to screen if we screen in a very high risk population, target population where the prevalence is high, then this screening will be able to yield a good number of true positives. But if we use this screening test with such values on a low prevalence, like for screening a low prevalence disease, it will be a wasteful use of resources because we will be able to yield only a very few true positives given the amount of effort that we are going to given. Therefore, if a high risk population can be identified where the prevalence among those high risk population is high, then those people can be screened, then the program will be far more productive. In this MCQ, the examiner actually wants to test your understanding of the relationship between the predictive values and disease prevalence. So they per se, you do not actually need to do this calculation at all to solve this MCQ. I did this so that you can have a visual understanding, right? But if the MCQ options are such that they are giving the options that you need to, like this is going to be the PPV is 17%, the PPV is going to be 95%, the NPV is going to be 12%, the NPV is going to be 55%. Then obviously you have to calculate the PPV and NPV. So you can do directly by these formula which I have given on the screen. So you can just put in the values and you will directly get the PPV, NPV, and the diagnostic accuracy of the test in a given population, right? Now, predictive values of a screening test are frequently given as a short note, as a practical epidemiological exercise, and a favorite Viva question in both MBBS and MD examinations. So, if you want to develop a core concepts and keep yourself updated and ahead in the race, reach out to us at Medcom Academy. The details are shared in the description. Thank you very much.